She hasn't contacted me. And her, her phone number's canceled. She gets no. Her cell phone is. Maybe
office because I have my office. Come up right here on the. You come in, just put her, pile them up here on there. Okay. All right. Okay. So I haven't turned in the names to the wherever I turn them into, to get you on the class list. But but let me. So the people I read last time who were on the waiting list are in, as I said last time. Okay. And we had 8 new people show up last time, and we at this point in time have 4 spots. Okay. So now I'll tell you what happens, and I'll find out today. I mean, I said, I'll check who turns in homework today. That'll be the next gate, okay, right? So if you didn't turn a homework assignment in today, I assume you're not in the class. So that will be so I'll find that out today, and then what I'll do is I'll then turn in the rest of the names. My guess is what happens is people will drop. So if you 4 here who I haven't added in yet, I mean, it's never happened that at least 4 haven't dropped as they see what's involved, right? And so my guess is no problem, but I can't guarantee it, right? But it would be the first time ever that I haven't had more than 4 drop. Okay, so let me read the 4 and 4 that so far so the 4 new ones that I've added, okay, are in for sure, I guess, are Farzad Eskafi, yeah, Subramanian Venkatram, Robert James. Oh, see, that solves the problem right there. So we got 1 less now. Okay, right. All right. So, Chuck T. Lowe, okay, and since Robert James is not here, Albert Wang, okay, right, so okay. So that leaves 3. So already we're doing well. So my guess it won't be a problem for the final 3 there, okay. But what I'll do is put in that list for everybody, and maybe the final 3 will also get in if I see there's no homeworks coming in from more people. Okay, any questions about that process, which is now nearing its completion? Okay, good. Let's see, what are other things? Any questions about what we're... This thing is having trouble today. That's a problem. Any questions about the material went over last time, or how the course runs, and that kind of stuff? All clear? Good. Okay. All right. I'm going to be rolling pretty fast today with a lot of material, so please try to remember to stop me at halfway point, okay? How about like at 5 to 12? If someone can remember to, please stop. Okay, right. No more, okay, right. All right. Well, we started last time. Let me just say a little bit about the homework assignment. I had a number of people come up in office hours today, and were concerned that which was the point of the homework assignment. That you have these curves, right, and you'd take points off these curve, and points on one curve wouldn't fit the points on the other curve, and so on. That data you have is real data. I mean, that's off real transistors. Okay, so this is 0.13 micron, real process. The issue that you're seeing was level 1 doesn't have enough of the physics of the actual model to actually model what's happening in those transistors. Okay, that's not surprising. Level 1 is a very simple model. It's actually basically the hand calculation model we talked about. It doesn't even have, as you noticed, the subthreshold stuff we talked about, which is kind of a pretty elementary thing. So we're going to go to level 2. Okay, and level 2 basically has this subthreshold region, but it still doesn't do a very good job even in the upper stuff. Is that a problem? Not really. I mean, I guess what I really wanted to give you from that homework assignment is that in some sense you get this feeling of this 10% approximation I talked about. I mean, given the accuracy, if you went in by hand calculations and calculated things to 3 decimal places, figured out all the currents, figured out all your gains for that kind of accuracy, all you have to do is remember back to this assignment we just did, right? That the underlying model that you're using for your hand calculations isn't that accurate, right? I mean, I think it's BSIM5, or someone know what's the most modern BSIM model right now? I think it's 5. There's like 250 parameters in that model. Can you imagine doing hand calculations with 250 parameters, right? Obviously impossible, right? And so there's no way that we can actually use the really accurate model that really models all of these transistors over all its current and voltage ranges, okay? So, but in actual fact, it won't matter that much, okay, in the end. The way we use these circuits and the way we will do setup biasing, we will set up things in such a way that we're relatively independent of the actual exact value of the model. So in other words, when you do your project, and here will be a little challenge for us to set the project up in such a way that you don't end up setting some parameter to 3 decimal places, and that makes your circuit work, okay? Because that's obviously something that's totally unrealistic, because the underlying model isn't that accurate by any means, right? I mean, so in actual fact, a good design, quote, good design, will be something that's independent as much as possible of all the parameters of the process, okay? Now we can force that, we can make you deal with that issue, and all we have to do is say, okay, there's 3 SPICE models. This is typically how people do design. They'll have a typical SPICE model, with values for gamma and VT and so on. They'll have a fast one, and they'll have a slow one, okay? So you have these 3 models that you have to make your device, your circuit, work over. In other words, you have to do your design, put in the try it, simulate it over these different skews of the process, in effect, okay? In fact, it's even a lot worse than that. Typically what happens is it's more it's finer granularity. Often what people do is they'll have 3 sets of parameters, okay? They'll break the parameters up not just into one group and call it fast, have another group call it slow. They'll have 3 different sets. Each one of those sets can have a fast, typical, and slow sets of value. So then you see a matrix of 9 things that you possibly can have, okay? And so you can look at corners. You can look at fast, fast, fast corner. You can look at the slow, slow, slow corner. You can look at the typical, typical, typical corner, right? Or combinations of in between. All of a sudden, you can sort of see now the design process is getting pretty complicated now. If you have to sort of figure out if things work over 9 different SPICE files. But in actual fact, the way you do it is you make sure that the circuits you have are just independent to the most degree that you possibly can of the underlying model. And that's what a lot of stuff we're going to do in this course. And you'll find that we're able to do it to a large extent. Okay. So hopefully, I think that was a good homework assignment. I think a lot of you got, at least the questions I was getting in office hours, you got the point. I mean, the point is, we're not, just reiterate, those curves that you're getting are real transistor curves. I mean, so that's, you get out in industry, you're not going to you'll get stuff that's like that, okay? So you can sort of see what you're having to work with in the real world, okay? And so it's more complicated than just those simple equations that we're going to use for most of our design. Okay. Any questions about that? Okay. All right, so let's go to circuits. Okay, so we're going to do, hopefully get through several of these today. The one we're going to start off on, okay, is this guy right here, okay? This is the common source. Here's the transistor, here's the input, here's the output. I'm going to, remember there's 2 parts of every circuit we're going to do. We'll do the large signal analysis, then we'll go over and do the small signal analysis. So I'm now doing the large signal analysis, and you can sort of see I have large VN, VB, these are DC voltages, okay, DC V0, okay, ID, large uppercase, that means it's a DC current. Notice I also have this little V0 here, that's the small signal. VN, that's the small signal value. Notice the DC and the small signal values are in series with each other, which makes sense. The way to think about when we do the large signal analysis, all the small signal parameters are set to 0. Okay? And effectively, when you do the small signal analysis, okay, all the large signal parameters are effectively set to 0. Okay? So that's the way we take them out. In other words, when we do this large signal analysis, the little Vn here, which is the small signal Vn, and the gain, small signal gain we're talking about was V out over Vn, we'll assume we do the analysis initially that Vn is 0. I mean, it's a small, microvolt deviation on the DC value, so it makes sense you could just ignore this when you're doing this DC analysis, okay? What may be a little more confusing is when we do the small signal analysis, why do we set the DC parameters to 0? What we will do is get all the parameters of the small signal circuit, the little R0, the little GM, the GMB, okay? Once we get those parameters, we'll get those, they're a function of the DC parameters, the DC current primarily, right? Once we get those values, that's the way we include the DC operating point, okay? And so we don't explicitly include it anymore. And so what we will do, we do the small signal analysis. VDD will be set to 0. It'll be set to ground, okay? If we had a current that was biasing something, okay, that will become an open circuit, okay? The current set to 0. So we do small signal analysis. We'll set these DC parameters to 0, and we'll have a small signal circuit that it will look a little bit weird, but remember, we've already taken into account how the DC, it's not that VDD is 0. If VDD is 0, I mean this device would be in cutoff or linear region operation, right? So we've actually included the effects of what region of operation we are by how we've included it in calculating these values of R0, GM, and GMB, and we do that during the DC analysis, okay? So that's the big picture. So we'll do this now explicitly for this kind of circuit right here. Okay, so it's common source. This is our gain stage. This is the way we get gain, okay? Here's the driver transistor. Here's the input on the gate of that driver transistor. It's relative to the source, which is grounded in this case. Okay. You take the output off the drain. Okay. And this is the load. This drain resistor is the load. We will change what the load will be. In fact, the typical circuit that we will use is a current source up there. And we'll get to that fairly quickly. We have to do current sources before I can do the circuit, right? But we'll put a transistor current source in place of that resistor, and that has some huge advantages. We get a lot more gain if we do that, okay? So this circuit right here, this common source stage, is our gain stage. So it has high gain. What's high? High, moderate, low, what do those things mean? Well, it's obviously all relative, and it also is, dependent on what the process we're talking about. So you need to get a feel for those things for CMOS, okay? And also to give you numbers. High gain is something like 100 or more, 1,000. That's high, really high, right? 10, 5, 2, that's kind of moderate gain, not very much. Gain of 1 or less is low gain, okay, or loss, right? Okay, so, gain of 10 is kind of moderate, gain of 100 is kind of high, gain of 1, 2, 3 is low, okay? Moderate R out. This is the output resistance. Now we're talking about small signal parameters here, right? This is small signal parameters, okay? Moderate R out means the output resistance looking back into this output node here. This is the output of our two-port. This is the output resistance of the two-port network we're talking about here. A moderate value of that is something like tens of kiloohms, okay? Kiloohms, tens of kiloohms, maybe 100 kiloohms. High would be megohms, tens of megohms, hundreds of megohms. That'd be high. Low would be 10 ohms. So if you get a feel for that, okay. So obviously this is pretty fuzzy stuff, but get a feel for what's high, what's low, what's medium. So when you get your answer, if you do an output stage, if you do a common source stage like this, and you end up with an output resistance of 3 ohms, whoops, something's wrong here, right? That's not moderate output resistance, that's low. Something's fouled up. Probably your transistor here is in linear region operation then, or something like that, okay? That would be weird. All right. Okay, yeah. Okay, repeat the numbers for our out? Yeah. Low. Low is something like below 100 ohms, okay? Moderate is something like kiloohms to tens of kiloohms, okay? High would be like megohms to hundreds of megohms. Okay. This device here, depending on what the output voltage is, you can see what region of operation it's in, right? Now, as we sweep, this is VG here, okay, this is VN, right, which is VN, right? I guess it's VB, I guess, in this plot right here, okay? So this is the input voltage being applied to the gate, okay? And if Vn is less than the threshold voltage, right, and this is Vt0, since there's no body, we assume that the body of the NMOS device is tied back to the substrate. I've explicitly shown it here. Often I will not show that, but you assume it if I haven't shown something else. If it's less than Vt0, we're in cutoff. If we're in cutoff, what's IDS? IDS is 0. If IDS is 0, if there's 0 current through this transistor, that means there's no ID equals IDS, right? This is IDS here, right? ID will equal IDS because no place else for the current to go. That means there's no current going through this resistor. No current through this resistor is no voltage drop. So that means this voltage here is equal to VDD. So you start off at VDD. So when you're in cutoff, if this input's below VT, threshold voltage, then you're in cutoff. So as we start increasing this voltage, increasing VB, increasing VN, then what will happen, this device will turn on, current will start to flow, current starts to flow here, ID equals IDS, so we begin to get some voltage drop across that resistor. So the voltage at output, V out, equals VDD minus IDS times RD. So as IDS gets larger, we start dropping the voltage, and here we go, we start dropping the voltage. We'll be in saturation initially because we got a lot of voltage across this transistor, right? I mean, if this VDD is all reasonable, and what do we check for? We look to see if the voltage VDS, what's our check? What's our check to see if we're in saturation? Courage. Let's have some courage here. All right. VDS greater than VGS. What's an easier test? What's the test I talked about that I said that the one you really got to get used to? It's an easy one to look for. Easy one to check. Okay. Open your brains. Remember this. All right. The test is VDS needs to be greater than VDSat. Okay? That's all you got to test. All you got to find. So what is VDSat? VDSat is equal to this is 2 IDS over K prime times W over L all to the 1/2. So once you know IDS, you can calculate VDSat, right? And you can easily find if this guy's in saturation. Okay? And how do you find out what IDS is? Well, you can, if you know what V out is, you can easily find it out. Okay. So that's the test. Okay? Remember that. Just look to see if the voltage across the drain to source is greater than this VDSat value. If it's less than that, you're probably in linear region operation. Okay? Now, as soon as this, as we have more and more current flow through this, we keep dropping the voltage lower and lower. And soon as we get to the point where this voltage here, this is VDSat, right? Soon as that output drops below VDSat, then we go into linear region operation. So this is V out here, right? So this is V out equals VDS, right? Because V out is just the same as VDS. So as soon as that drops below VDSat, we're in linear region operation. So it's pretty easy to check. Right? We want to operate in this saturation region. This is where the gain is. You can see down here we don't have any gain, and here we don't have a gain up here. So we need to operate in this center region here. Okay. Alrighty, let's see. Anything else? What's going on right here in this little bit of this little curve there? You know what's from your problem you just did? What's causing that little round off there? If the saturation equation is always the same all the way through here, how come I show something different right up there? You takers? You know what? Good, thanks.
Is it subthreshold?
Exactly. Good. Right. Yeah. This is the subthreshold region. This is the region right near VT. So we're beginning to, so this, if we didn't have subthreshold, this thing would look like, come out here and then just have a discontinuity at that point. Okay? Right around VT. Okay? We don't have discontinuity. You know, nature just doesn't have sharp things happen. It always kind of smooths everything out, right? And what smooths this out is saturation. I mean, it's subthreshold. Okay. So let's do a DC analysis. Let me redraw this so typically, actually, what I do in the notes is a little bit weird. So I'll go back and show you this in a second. I was kind of wanted to show you this iterative solution, but let's do the typical DC analysis calculation you would do for this circuit. Okay, this is RD, and let's say this is VN, and let's say this is V out. Okay, so VN equals VB. Remember, that's the bias voltage. Okay, so let's say typical question might be, this is 5 volts. Okay, you want to probably, typically you'd like to, remember a curve looks like this, right? And this is V out versus Vn. So this is the whole curve. We'd like to bias ourselves sort of in the center of this region of operation, because if we have excursions around that, we don't hit clipping on each of these two ends. We don't go out of the saturation region of operation. So bias yourself in the center, typically what you try to do. What's the center? Well, here's 5 volts here, so we'd like to bias ourselves around 2.5 volts. That put ourselves right in the center of this, 0 to 5 volts. Okay, not exactly right, because here's a VDSat here, so the exact center would be, say this is 0.1 volts, right? It would be a little bit less than that, but let's just say typically, roughly, it's 2.5 volts. So our problem is, what is Vn or V bias to bias our output at 2.5 volts? How would we calculate that? Okay, so that's what I'm going to do. All right, here's IDS. If the output's at 5 volts, that means we have 2.5 volts dropped across the resistor. RD we said is equal to 1K ohm. So 2.5 volts. So IDS has to be equal to 2.5 volts. That's the drop across resistor divided by 1K ohm, or 2.5 milliamps. Okay, so that tells us what IDS has to be, because we know how much voltage drop we have to cross RD. We could now check to make sure we're in linear region. We could calculate VD sat. Okay, VD sats are going to 2 IDS over K prime W over L, okay, to the 1/2. We could calculate this value. I don't know what it is. Let's say it's something. Probably going to be less than 2.5 volts, okay? So we could check to make sure we're up in saturation. So there'd be our test if we wanted to do that. Notice what I'm doing. I'm assuming, what I'm going to do now, I'm going to assume I'm in saturation. Okay. Now, what is the formula for saturation? Okay, the formula for saturation is equal to IDS equals K prime over 2 times W over L times VGS, but VGS minus VT, but VGS here is equal to this VN, right? So I'll just put in VN here, okay? Minus VT, quantity squared. Let's put in the full thing, 1 plus lambda VDS. Okay, now VDS, we said for this, VDS is equal to 2.5 volts, right? 2.5 volts across the resistor, 2.5 volts across the transistor. So VDS is 2.5. So is this term important? Let's check. Lambda, we said here, was equal to 0.01. Okay, 0.01. 0.01 times 2.5 is what? 0.025. So this term here is 1 plus 0.025. Can I ignore that? Why can I ignore it? Less than 10%, right? Bam, it's gone. Okay? Let's just not deal with that anymore, okay? Right? Actually, leaving it in there would be kind of a mess. It'd make this thing a much more complicated problem to solve. Okay, so get rid of it. Okay, so now we're down just to this part right here. Okay? So now we need to calculate what Vn is, which is equal to Vb. And you can, and what's our answer going to be? So here's, let's say I calculated VD sat. I don't know if someone do this for me. There's a value here, right? Okay, so VD sat's a number we can calculate with this 2.5 milliamps in here, okay? I'm not sure what the number is. If we've already calculated VD sat, what is the Vn which gives us a current of 2.5 milliamps? Right, tell me what that is? Okay. Part 2 of opening the brain with VD sat. Okay, right? First thing VD sat was good for was checking to see if we're in saturation. The second thing it's really good for, and it's kind of a very different use of it, right? But remember what VD sat is defined as. VD sat equals VGS minus VT, right? VGS for this problem is Vn, right? So Vn equals Vt plus VD sat. So VD sat, once you have that value, it's the voltage above the threshold which supports the current, okay? And that's why the book calls this V overdrive, okay? Right? It's the voltage above the threshold that gives you more. The larger VD sat is, sort of inverse way we thought about before a second ago, is the more current we have. In other words, you start with this Vn. When the Vn's 0 volts, no current at all. You start increasing Vn, you get up to Vt, current starts to flow. As you get above Vt, that's the overdrive. This is the additional voltage above the V threshold value that drives current. And that value is VD sat, and its formula is just right here. Right? So basically, once we have VD sat, we know for a given current, we know what the Vn has to be. It has to be equal to V threshold plus VD sat. Right? So once you calculate VD sat, you can sort of use it at a bunch of different places. Right? That's kind of nice. All right. That is, so got the procedure here for DC analysis of this simple circuit. Typically, you're given the V out. From that, you can find the current. You can find the IDS. Once you have IDS, you can calculate VD sat. Once you have VD sat, you know what the input has to be. It has to be that VD sat above the threshold value. That's the DC analysis. Okay? Not too complicated. Right? Now, often, this is kind of straightforward. There's no quadratics or anything. Sometimes, depending on how I structure the problem, you can end up with a quadratic you have to solve, right? And the way that can happen is, I guess for this case, it would be, let's say I gave you, well, I mean, the other problem I could give you is, given the VN voltage, what is V out? How would we do that? That'll be pretty easy, right? Given Vn, I could plug into this formula right here, K prime over 2W, Vn minus Vt squared. If I know what Vn is, I can calculate IDS. Once I know what IDS is, then I can calculate, this voltage drop is equal to IDS times RD, right? So I can figure out what V out is. So that's still straightforward. There's no quadratic to solve. What I did in the notes is I said, let's calculate this point right here. That wasn't me, right? What's this point right here? What's this edge of saturation? What's this voltage that goes between? Well, it's when V out is equal to VD sat. But what's its value on the V in side? That turns out ends up to be a quadratic. Do you often solve for that? Not really. I mean, you might want to know what that is to see how big a signal swing you can have on the input in order before you go into linear region operation, because that tells you. As soon as you go out of linear region operation, we'll call that clipping, or typically what's going to happen is the output signal, once you swing so large, the input swings so large, that you get out in these regions, the output will be distorted. Okay? In other words, if I put in a sine wave at the beginning here on the input side, and if it stays inside this region of operation here, the saturation region, on the output I'll see gain and I'll see a bigger sine wave come out. When I keep increasing that input, making it bigger, what will happen finally in the output will clip. Because what's happening is I'm making excursions up into this region of operation up here. And what's happening, the gain is dropping dramatically when that happens. Okay. So this is nonlinear distortion. We'll typically try to keep ourselves looking like this, right? We don't want to do this. Our circuit's no longer working properly. Okay. All right. Let's see. Okay, so you can look at the notes here. I solved for this. Probably the one step I missed here. I said here's V out equals VDD minus IDRD. V out equals, so I just substituted the equation for ID, IDS, our typical quadratic equation. This is the test for the edge of saturation, which is this point right there. V out has to be equal to VD sat at that point. So I use that point. So V out at the edge of saturation is equal to VB minus VT, which is the edge of saturation, right? That's equal to VD sat, right? Then you have a quadratic here. VB minus VT on this side equals VB minus VT squared on this side, so you've got a quadratic. One way you can do this is solve this iteratively. I always show this to you guys, and no one ever does it. So what everybody does is they go in and they solve the quadratic formula. Well, that's fine, too. I don't care how you do it, right? Sometimes you'll end up with quadratics. Sometimes you end up with cubics, and then you're toast, right? And so then you've done the problem wrong, right? So I won't ever give you a problem where you have to solve a cubic, right? And but often you might end up with not often, occasionally end up with a quadratic thing. But you know the quadratic formula, you can solve it. Okay, that's DC analysis. Step 1. Okay, now we go to small signal analysis of this simple circuit. Okay, any questions about DC analysis? Okay, all the small signal parameters. So now we're going to do the small signal. We'll redraw our circuit. Remember our circuit our real circuit is this, right? Here's a resistor, here's our transistor. And now what we're going to do is set all our DC parameters to 0. So small signal, I'll set VDD to 0. I'll set, here's our little V in. So I'll set VB to 0. Okay, here's RD. When I've done this, I no longer now check for large signal characteristics, like what region of operation I'm in, right? I mean, small signal voltage applied to this gate means this thing, if I didn't have a bias voltage, this thing would be in cutoff. But I don't care. I'm doing the small signal analysis now. Okay? The DC VDD is set to ground. Just like I set the small signal 0 before, now I set the large signal independent bias voltages to 0. Okay. Now, let's go. Now I'll replace the transistor here with that model we developed last lecture. Here's GM-VGS, GM-B-VBS, and R0. Here's the gate coming in. Here's the gate coming in, goes nowhere. Here's RD off the drain. It goes up to ground. Remember, because it's the small signal stuff now. Okay. I crossed out GM-B-VBS here in my notes. Why did I do that? VBS is equal to 0, right? Okay, VBS equals 0, right? Because the bulk is tied to the source, and that's VBS is the value, the voltage from the bulk to the source. And so if I don't show it anything explicitly and the source is grounded, you assume the bulk is tied to that. Okay. So this current source is gone, okay, because VBS is 0. Okay. So now we end up with GM, VGS, and R0 in this resistor, and that's the circuit we got to analyze. If we have V out equals 2.5 volts, like I assumed a second ago, ID is 2.5 milliamps, as we talked about. I can now go in and solve for R0, right? And I can solve for GM. Where did I do that? GM equals 2K prime W over L IDS to the 1/2, right? Okay, so I can get my GM value, I can get my R0 value. That's the only two small signal parameters left, and it's a function of the DC current that I calculated in that first part of the problem, the DC analysis part of the problem. Okay, so what's V out equal to? Well, it's pretty easy to solve this problem, right? Now, okay, now here we do some things. Okay, it's pretty easy, but let me just do it. So let me redraw this here just so it's easy to see. Now remember I said this last time, you don't solve any problems that you already know the answer to. Okay, and here's GM, VGS. I assume you all know what the parallel resistor problem solution is. I'm not excited at all to see that you can resolve that problem, okay, right? So what can we do right off the bat here to simplify this circuit? We can redraw this with V in here. This RD goes to ground, this R0 goes to ground. So that means RD is in parallel with R0. So I can redraw this circuit like this, where this is RD in parallel with R0. This is ground. Okay? And this is GM VGS. Yes, use a mic. Use your mic. Push a button. Yeah.
It doesn't make sense to me that you tie the source to VDD.
Tie the source to VDD.
Well, because you set VDD to 0 and set the voltage, the other end of RD to 0. That means that you are saying the source is at the same voltage with the...
Okay. Good question. I admire your courage for asking. Okay. Two parts to this analysis, okay, right? So now you got to just flip yourself right now. Soon as you do the DC analysis, which has VDD in it, okay, then you get all the currents and DC voltage. You check for region of operation. When we move over to the small signal analysis, we take all those sources in the DC analysis and set them to 0. So they're all, as far as we're concerned in the small signal analysis, they're all 0. So 0 equals 0, and so the fact that it used to be VDD doesn't matter to the small signal analysis anymore. It's now 0. And ground is 0. VDD, it's not there anymore. It's just not part of this part of the analysis, right? You get it? That's really an important point, because until you get that two different types of analysis clear in your mind, you're going to make mistakes. Okay, right. Okay. So here we are. So we set it to ground. Everything. So we just look at this circuit here. Just forget how I got there. I mean, just believe that circuit. That's ground. That's ground. So these two things are in parallel. That's the way I think about it. Okay. What is V out? Well, V out's pretty easy to solve now, right? This is just a little loop right here. We can see that all of this current has to drop across this. So V out is equal to minus GM VGS times RD in parallel with R0, and VGS is the voltage here, so VGS equals VN, so V out equals minus GM RD in parallel with R0 times VN. V out over VN is our gain. Now I'll show small signal gain as an uppercase A, okay? So that's a little inconsistent with my uppercase. So voltages and currents are all uppercase for DC parameters. It's lowercase for small signal, but small signal gain, input resistance, and output resistance will be uppercase. Lowercase R0 and so on, those are the parameters of the transistor, right? So that's kind of why we do it, okay? That way. So AV is equal to what? Minus GM RD in parallel with R0. Okay, let's go back and look. R0 I calculated, lambda was 0.01, 2.5 milliamps. R0 is equal to 40 kiloohms. So this is equal to minus GM times 1 kiloohm in parallel with 40 kiloohms. Do I need to do any calculations to find this value exactly any better than this? I mean, what's the answer to 1 kiloohm in parallel with 40 kiloohms? 1 kiloohm, right? To within 10%, it's 1 kiloohm. Forget about the 997, ohms or something like that, right? Just don't go there, okay, right? So this is equal to 1 kiloohm, okay? All right. GM we calculated, and it was out equal to, apparently we did it right somewhere. So we plug into this formula right here, and I'll tell you what the answer is. It's 1.2 times 10 to the minus 3. Okay? Plug in that formula. So we can plug into here. So we have minus 1.2 times 10 to the minus 3 times 10 to the cube. This means it's the gain of minus 1.2. Okay, is that high gain, low gain, or medium gain? Low gain. I said this was a high gain circuit. What's wrong? It's a bad circuit design. Okay, you don't want to do this, all right? So whoever did this design was not a good circuit designer. Fire him. Okay, right? So this should have lots of gain to it. The fact that it has a gain of 1.2 means we're not getting a lot of gain. But why are we getting such low gain? GM low, I mean, there's two things that come into this, GM and the output resistance, or the resistance, right? What's causing the gain to be so low? It's the RD that's so bad, right? GM, 1.2 milliamps, clearly the GM goes up with current, right? 2.5 milliamps is a lot of current. A lot, okay? Typically, we will use current levels on the order of more like 10 to 100 microamps, okay? So 2.5 milliamps is really blasting that little transistor, okay, right? So in that one transistor alone here, if you have 2.5 milliamps flowing through here, how much power is being dissipated in that circuit? Who can tell me the answer to that? 5-volt DC supply, 2.5 milliamps of current, how much power? How much? 12.5 milliwatts, right? VDD times IDS, right? That's how much current's flowing through here. VDD times the current out of that supply is equal to 12.5 milliwatts. We'll have entire op amps that'll be like less than a milliwatt, okay, with 20 transistors in it, right? 12.5 milliwatts for one little stage like this is just, we're really pumping a lot of current through that guy, okay? So get used to that kind of numbers. When you do your designs, when you get your designs, you're going to have, you could be able to choose any current you want. You could start with 1 amp if you wanted to, right? That's a lot of current, right? 12.5 milliamps is a lot of current, and amps are really a lot of current, right? And so basically what you'll do is you'll try to get a feel for what numbers you're going to use, because I'm not going to tell you what current to use. You'll have to optimize over a lot of different parameters, and you'll choose what values you want. I'll give you a little insight now. If you end up using tens of milliamps, you're probably using a lot of current. You better have a reason to do it. There might be a reason to do it. The reason you might want to do it is because you have to drive a lot of resistance, or a small amount of resistance. Sometimes you need to have a lot of current, but often you don't. I will stop myself, okay? You don't have to do it for me. Okay, so we'll take a 3-minute break. How's that? Okay. I'll get a drink of water. You are now. Conductance of the circuit, okay, as opposed to little g sub m, which is the transconductance of a transistor, okay. So what is the circuit transconductance? The circuit transconductance, and how do we calculate it, is we do it like this. Take Vn, let me redraw the whole thing. And what we want to find out, and this is grounded here, right? This is a small signal now, remember? That ground all thing. What we're interested in finding out is the output current of this circuit. Okay, now to calculate the output current, in order what we need to do, right, is we have to drive it into a short circuit. In other words, when you calculate the output voltage, you assume you're going into an open circuit. You know, if you assumed you had a short circuit on your output when you're calculating voltage, you always have zero, so there'd be no gain, right? So it's kind of what it's sort of, what we're doing is a two-port here, and we're doing, and basically the two-port is this, right? So now we're calculating, this is Gm times Vin. Here's Vin, here's V out, here's R out. So this is the two-port we're solving now. In order to find out what big Gm is, what do we have to do? We've got to get rid of this R out effect here, right? To get rid of the R out effect, what we do is we short this, and then the current flowing here will be exactly equal to Gm times Vn. So that's what we're doing, right? So how do we do that in our circuit? Well, we take the circuit and we short this, and we calculate the current here. And that'll be this current flowing right here, right? So you see what we're doing? So this is how we're trying to find out what this big GM value. Then we'll have to go back in and calculate R out. Okay, we'll do that a different way. But right now, this shorting this gets rid of R out. We can calculate what big GM is. And this shows why, and typically calculating big GM is really nice because of this fact that you're shorting this output. You get rid of this, a bunch of stuff that's hanging on the output node, right? If this is shorted, how much current is going to go through RD? Zero, right? So effectively RD is out of the picture now. Okay? So it's even a simpler problem. So let's do our small signal circuit. And okay, we have R0 here. Okay, and we have a short here. So this is the I out that I'm going to calculate. Okay, so how much current is going through R0? This side's connected to ground. This side's connected to ground. Zero voltage drop across R0. How much current is going through it? None, right? So it's kind of out of the picture too, right? So our circuit kind of degenerates down to simply equal to I out equals minus Gm times Vn. Big G sub m is equal to I out over Vn when V out is set equal to 0. That's kind of our condition. What's that equal to? It's going to be equal to minus G sub m. So the circuit transconductance of this circuit is equal to minus G sub m, minus the small signal device transconductance. Okay? Little sign change there. This is an inverting circuit. I should mention that. You know, this circuit inverts. You know, Vn comes in, you get minus the gain times the input for the output. Okay? So you can sort of see it makes this problem a lot easier to solve, right? I mean, you just GM, and often this happens. You know, it's easier to calculate big GM. Let's say I really want it as AV, though. I really want V out over Vn. I don't want this G sub m thing, so how do I get that? And remember the way we did that was we compared the two. Let me go back. Where was that? I think it's this little analysis. It's a few pages over. Excuse me. Here's the two ports we're working with. Here's this voltage in, voltage out two port. Here's this voltage in, current out. And these are equivalent ways to analyze this circuit. I mean, the two-part part here. We can describe the two-port either of two ways. Getting the parameters inside this two-port are done differently, right? To calculate big G sub m, we short the output to find what G sub m is. To find out what AV is, which we just did a minute ago, right? Now here I used AV small. Yeah, sorry about that. So little AV here is equal to big AV as well. Right? Okay, definition. Right. So this is the circuit gain. Okay. So now how do we go back and forth between these two? Let me make this big AV, make this big AV, make this big AV. How do we go back and forth between these two? We can see that if we take this circuit here and calculate what the voltage here is going into an open circuit, which is V out, we can see that V out for this 2-port is equal to this. All this current will have to go through this resistor right here, will be equal to big G sub M times R out times V in. So this here is equal to, and if we look at V out here, we can see that this open circuit, there's no voltage drop across R out, so the output here is equal to AV times V in, so this is equal to AV times V in. I can see this fact that I short this or open this is when I'm trying to calculate the parameters inside there. Once I get those parameters inside there, I can then use this 2-port in any circuit I want. And what I'm saying is that I can use this 2-port to calculate the open circuit output voltage. And what I'll do is I'll look and see what it is, and I get this value right here, GM times R out, to calculate the open circuit output voltage. I can also use this circuit if I wanted to calculate the short circuit current. How would I do that? Well, I short this, find out what current flows here. What current flows there if I short that? It's going to simply be this voltage over this resistor, right? So I out is going to be equal to AV over R out times V in. AV over R out is the same as GM times V in, right? So you get the idea? So this is a voltage input, voltage output 2-port, voltage in current output 2-port. They both can be used to describe the circuit. They're both equivalent, simply a Norton to Thevenin equivalent transformation here. But when you calculate the values inside that 2-port, you do different things to the output, right? For this one, you short it to find the current, and for this one, you open circuit to find the voltage. Get that? This business about voltage in, current in, voltage out, voltage in, current out, is going to hit you big time when we do feedback towards the second after the midterm. Then we're going to work with all 4 combinations: current in, current and voltage out. And it's going to be, and we'll have to do appropriate things like this: short this, short that, and so on. So if you can get used to this now, this is the only case we'll have up to the midterm. But try to get clear on it now. If you're calculating this sort of current output 2-port, where you have a transconductance inside here, then you short the output to be able to calculate what big GM is. And you just go do this to your circuit. I mean, basically the strategy is just go to your circuit and do exactly the same thing. And you can find what that GM is. Okay, so now we see GM times R out equals AV. So I found what GM is. How do I calculate R out? And remember we did that earlier. We talked about this first lecture, I think, on calculating how you calculate R out. The way you calculate R out is, for a 2-port like this, is okay. Let me redraw it again. So here's the definition of R out. It equals 2. The way we'll calculate this is we'll take a test current and force it into the output. When we force that into the output, we will generate a voltage, V test. R out is defined as V test over I test. What do we do with the input here? It's defined as V test over I test, where all the independent small signal sources are set to 0. So V independent, okay, for this case is just one independent source, which is equal to V in, and we set that to 0. If we had a current source over here, a little independent small signal current source, we would set it to 0. Setting a current source to 0, what does that do? That means you open circuit it, right? No current means open circuit. If we have some dependent sources, we don't mess with those. Okay, dependent small signal sources, they may change our answer. It's all the independent sources we set to 0. So for R out, we can force a current and look at the voltage which is generated. Equivalently, we can do this. This is exactly the same as doing this, of course. Let's force a voltage and measure the current. So you have a choice. This is up to you. If you want to calculate R out, you can either force a current, calculate the voltage, or force a voltage and calculate the current. Why do we use this as R out? If you think about what an ohm meter is or something like that, right? How does an ohm meter work? When you take an ohm meter, you put it to a circuit, okay? What is it doing? It forces a voltage and it looks at the current that flows. Okay? So what we're kind of doing is an analytical ohm meter. Okay? This is kind of a rigorous definition of this thing. We force a voltage, we see what current flows. Well, that means all of this circuit then can be replaced by an equivalent R out. So that's what we're trying to do. We're taking all this complexity here, which isn't too much in this case, but it's going to get worse. We're taking all this complexity and turning it into be just a simple resistor. And that makes life easy for us, because then we can sort of work with that to do other things. We don't have to, as soon as we get this equivalent resistance, we don't have to worry about the fact, is this thing in saturation, what's VDD, what GM, we don't have to worry about that anymore. Right? So that's kind of how we do this. What about the input resistance? We have to do a similar thing on the input. On the input, we can force a test voltage into our input. Okay, same thing. Rn is equal to, and what's I test, is equal to V test over I test with the independent sources to 0. Well, there's no other independence. So I mean, basically, there's no independent sources in this circuit, right? So what's the answer going to be for this? Well, we force a voltage into this gate. What current are we going to flow? 0, right? So Rn is equal to V test over 0, which equals infinity, right? And so, yeah, so looking at the input of a gate is infinite resistance. That's high. Okay. I didn't say high gain, moderate R out, and high R in, right? It's very high. It's infinite, right? Which is really nice. Okay, so let's go back and now do our output. Now these are what do I calculate here? Remember what I'm trying to do. This is the 2-port we're after. Here's R in, and here's, I'll do it as voltage 2-port right now, right? AV times VN times, here's R out. So Rn is equal to infinity. I can easily test that. Let's calculate what R out is. Okay? So let's go back to our equivalent circuit. Here's the equivalent circuit that I had. Let me redraw it for you. So here's Vn. That's an independent source, right? R out, remember our Vt over It with independent source equal to 0. So we force this voltage in this current or voltage into the output, and we set the independent source 0. Vn's an independent source, so we set that to 0. Here's our transistor. Here's our resistor. Here's our output. And what should I do, a current or a voltage? And let's do current. Your choice. If you work these problems before, you can probably choose some that are easier than others sometimes, right? I need to calculate what V test is. Let's do the small signal, replace this transistor with a real small signal circuit. What's it look like? Here's RD. It's going to look like, with the simplification that I did before, right? Here's GM times VN. Here's RD in parallel with R0. Here is my test current, and here's the test voltage that I need to get. Here's oops, I'm sorry. Oops. Here's VGS, which is equal to 0 now, right? We've shorted out this input here. And this input's grounded, right? So VGS is equal to 0. Okay? So if Vn's equal to 0, what about this current source? It's 0. So the independent source is 0. That means this dependent source goes to 0. Right? Because Vn's equal to 0 equals Vn, which equals 0. So now my problem simply becomes I force IT and I have this parallel combination of RD and R0, so what's VT equal to? VT is simply going to be equal to RD in parallel with R0 times IT. And we go back to our equation, VT over IT is simply going to be equal to RD in parallel with R0. And this is equal to R out. Okay? So that's the really slow way to do this this calculation. Now, why do we do all this? Because more complicated circuits, it's not going to be so easy, right? You kind of look at this thing, and you can sort of think, now here's the thing you're going to have to do. You know, notice I draw, right now I'm drawing these small signal circuits every time. As soon as you get a half a dozen transistors in your circuit, you don't want to be drawing these little small signal circuits, okay? So that's this point I was telling you. You're going to need to learn the answers to these simple circuits and not be drawing this, the small signal value. What you need is these answers. The answers being the gain, the G sub m, R in, and R out. Okay. So for this circuit, now let's finish up here. We know. So let me summarize. Big G sub m is equal to minus little G sub m. Calculate that, right? R out is equal to RD in parallel with R0. R in equals to infinity. What's the voltage gain? The voltage gain is equal to big G sub m times R out. Remember that? That's the thing we just talked about just a few seconds ago, right? That's going back and forth between these two different 2 ports. We can plug in here. Big G sub m is equal to minus little G sub m. R out is RD in parallel with R0. And remember, that's the same thing that I calculated a few minutes ago somewhere. I'm sure you have it. Here it is. AV equals V out over Vn, and I calculated this thing, and I don't know. I did someplace. Oh, here it is. V out equals minus GM RD in parallel with R0 times Vn. So here's where I just went after the open circuit output voltage directly. Didn't calculate this big G sub m thing, right? And I got the same answer. Here's the gain right here, right? It's minus GM RD in parallel with R0. Minus GM parallel with R0. I would suggest that the best way to do these problems is typically to calculate big G sub m, calculate R out, and use this formula to get the voltage gain. Okay? It's because you short that output, and that kind of simplifies circuits. Otherwise, you're kind of calculating R out twice, right? When you do this R out calculation, because you often want R out explicitly, so. Okay. That's the last time we're going to do such gory detail, you might guess, right? Any questions about that? That's the machinery. We're going to use this machinery over and over again. Okay, so get clear on it. DC analysis, small signal analysis, calculating GM, calculating R out, calculating voltage gain, calculating R in. We'll do this over and over again. Okay? Let's jump to here. AV equals GM times R out. We just talked about that. Equals GM RD parallel 0, just the things I was talking about. R0 is equal to 1 over lambda IDS. Now I'm going back. I'm connecting the DC analysis with the AC parameters here. I want to see what happens to this gain as a function of the DC current. Okay? Let's let RD be much greater than R0. For this case, it's not true, obviously, right? In this case, RD was much less than R0. It's the opposite. But let's look in the opposite situation, because we're going to have circuits that won't have such a small RD, because that's what killed the gain, right? And I'll show you how to do that later, but not today. If this is true, then the gain becomes minus GM times R0, and I'll call it the maximum possible gain. As I increase the value of this RD, the gain will go up and up until it becomes much larger than R0, and once that happens, that's the maximum gain I can get. Okay, so I'll call that AV max. GM is proportional to the drain current to the 1/2. Remember, it's 2K prime W over L IDS to the 1/2. So it's proportional to the drain current to the 1/2. R0 is inversely proportional to the drain current. So let's plug in this formula. IDS to the 1/2 for G sub M, 1 over IDS for R0. So I get a dependence on the maximum gain I can get if RD is very large compared to R0 as inversely proportional to the drain current. So what would you do to get lots of gain? Well, even simpler from this equation right here. Smaller current, right? That's what it tells you. This tells you, boy, use the smallest current you possibly can because you're going to get more gain. You'll get more gain until finally this is no longer true, because as you make R0 IDS small, R0 is going up. So what's causing this? It's causing because R0 is such a strong function of the drain current. It's inversely proportional to it, whereas the G sub M only goes up as the square root of the drain current. So you win. The output resistance goes up much faster than the G sub M drops as you decrease the current. Very important thing to think about in MOS. In fact, remember your bipolar stuff? What's the dependence of G sub M on current, collector current, for bipolar? Anybody remember that? Anybody know that? Someone knows it, come on. See, Bob Meyer and some of these other guys, they criticize me. You're turning out students who have no clue about bipolar. It was an important, people do designs with bipolar yet. It's not like it's so totally dead, right? It's like tubes, right? I mean, it took a long time for tubes to go away, right? Now bipolar's going away. But you should know your bipolar stuff. I'll have to. G sub M for bipolar, right? Who knows what the formula for it is? I collector over V what? V thermal, right? All right. It's proportional to the current. So for bipolar, you get a lot more G sub M for the same current. And that's a problem with MOS. This is not good, okay? If you want to drive a lot of current, you want to get a lot of current out, bipolar is better. And you can get, in some sense, with bigger G sub M, you can get more gain. So bipolar has more gain because of this lower G sub M dependence we have here. So why do we use MOS? Why is this whole course about CMOS? It's because of the integration. It's because of the fact that people are doing this, putting billions of dollars into fabs that do CMOS. And they're putting hundreds of millions of dollars into fabs that do bipolar, if that, right? And so it's just the enormous, emphasis of microprocessors and memory and everything else that makes MOS. But it's not good. I mean, MOS devices aren't as good as bipolar. They're noisier, they have less gain, but they're cheap. Right, and cheap is the name of the game, right. So that's what makes it work. Okay, yeah. In fact, here's the G sub M right there. Okay, 5 minutes. Let's do another circuit. Okay, right. So now you got the machinery. Now we can roll. Okay, right. Here's the new circuit. This is actually common source and with source degeneration. Now, what's this degeneration? Degeneration sounds like something bad. Well, it kind of is, and I'll show you what it is in a second, right? Here's the same circuit we had before, except now what we're going to do is we're going to put a resistor in the source. Okay? So it's not quite common source because there's a resistor sitting down there. Okay? What's the small... Now, let's do our DC analysis for a second here. If I don't show... I jumped right to small signal on this, right? I should have done my small signal, my DC analysis first, right? So here, let me do that. And here's big V out, okay? What is Vn going to be? Vn is going to need to be equal to Vt, the threshold value, plus Vd sat for whatever current we're going to have, right? Plus the voltage drop across this resistor, plus IDS times Rs. So if I set V out equal to some value, right? I take that divided by RD, then I can get IDS. Once I have IDS, I can calculate VD sat. I can calculate IDS times RS. Now, the close observer will see a problem here. Is this all that straightforward now? Is there something I'm forgetting? Do I just have to go in and calculate VD sat? Is the function IDS? That's a number. IDS times RS. Is that all I have to do? What about VT? VT now, if I have not shown it here, that means you assume that this then is tied back to ground, right? So now what I have to worry about is the fact that VT actually is now a function of VS. So VBS is going to be equal to what? It's going to be equal to IDS times RS. Right? VBS, minus that, I guess, right? The bulk relative, so it's minus that. So once I find IDS, I have to calculate new voltage here. Now I have, and which VBS, that means VT is not equal to VT0, right? I have to go through that big equation, VT equals VT0 plus gamma times 2 phi b plus VBS to the 1/2 minus 2 phi b to the 1/2, that whole thing, right? Or VSB, I guess. Okay, that's a DC analysis. We've done that. 1 minute. Can I do the small signal in 1 minute? Well, that's probably getting a little tight. So we've got the small signal, we've got the DC analysis. Then we redraw it like this. Okay. Let's calculate big G sub m before we go, okay, in the 30 seconds here. We short the output. Short the output, that shorts out this RD, so we don't care about that anymore. R0 is still in the picture, right? So what we have to worry about now is we write an equation for what this IS, and here's a little trick we can use. IS is the current through RS. How is that related to I out? If there's no voltage drop across RD, that means there's no current through there. Notice what I out does. I out comes out here, and I out, so these three, I out splits between these three leads and comes out on RS again. So I out equals minus IS. Right? Current here splits in three and comes back together again. So I'm just doing KCL on each of these two nodes. Right? And I just can get rid of that stuff in the center there. I out equals minus IS. So GM I can solve for minus IS over VN, same as solving for I out over VN. I write the equation for IS. IS VGS equal to VN minus VS. Here's VN, here's VS, right? So VGS equals VN minus VS. GMB equals minus VS. VBS equals minus VS. I can plug that in there. I write this little current node equation right here. Solve that, and I end up with this for the answer. GM is equal to minus GM over 1 plus RSGM times 1 plus chi. Remember what big GM was before without that resistor there? It was just equal to minus G sub m. Now I have this term in the denominator which reduces the transconductance. So putting this resistor here, reduces the transconductance, and that's why it's called source degeneration. It degenerates the transconductance. Okay, I'll do that. I'll do that again next time, but just make sure I got that to you. See you next Monday. New homework assignments out, so